The warm-up question for today says which has a greater acceleration, and it's multiple choice. You get to choose A or B. Option A says a car driving down the freeway at a constant speed of 65 miles per hour. Option B says a cyclist pedaling from rest to reach a speed of 10 miles per hour. You need to go ahead and answer this question in My Open Math for your warm-up for Unit 2. Find that assignment and go ahead and record your answer now. While you are doing that, I'm going to let you know that you do have an assignment for homework tonight. It is classwork with whatever time you have remaining after these notes, but if you don't have it finished at the end of the class period, it is homework. It is assignment 202.1, Acceleration Concepts Problem Set, and it is also in My Open Math. So hopefully you had a chance to think about the warm-up question. Which has a greater acceleration, a car driving down the freeway at a constant speed of 65 miles per hour, or a cyclist pedaling from rest to reach a speed of 10 miles per hour? And the answer you should have selected is B. This gets to the heart of one of the misconceptions students sometimes have about acceleration, and that is this: acceleration isn't the same thing as going fast. Obviously, a cyclist that is going from rest to a speed of 10 miles per hour is not going nearly as fast as a car driving down the freeway, but that's not what acceleration is. Acceleration is going to be the rate of change of your velocity. Okay, it's a vector quantity, but it's a measure of the change in the rate of velocity. So if your velocity is changing, you're accelerating. If you're moving at a constant speed, like the car was in the warm-up question, then you're not accelerating, even if you are going really fast. Acceleration happens when an object speeds up, slows down, or changes direction. Because it's a vector, if you turn, that is also an example of acceleration. And again, you guys saw this in the gizmo that you were doing last week, because some of you had a misconception that acceleration always meant speeding up. But it is also, you can have acceleration can also mean that you're slowing down. Here's another question to think about. Which has a greater acceleration? A car speeding up from 45 miles per hour to 60 miles per hour as it enters a freeway ramp, or a car slowing down from 45 miles per hour to 30 miles per hour in a school zone? I didn't quite give you enough information to answer this question. So let's assume that both of these two events take place over the same amount of time, maybe 10 seconds. Okay, and so if you're to answer the question, which has a greater acceleration, the correct answer would be that these two objects have equal accelerations, because changing 15 miles per hour faster or 15 miles per hour slower, we have the same magnitude. And that's what we're looking at, because when we talk about acceleration, okay, it can be speeding up or slowing down, or even just a change in direction. But the sign of the acceleration just tells us which direction our velocity is changing. So a change of 15 miles per hour, whether it's faster or slower, is still a change of 15 miles per hour, assuming that both of these take place over the same amount of time. Add this to your definition of acceleration in your notes. Acceleration is a change in the rate of velocity. It can be calculated by the formula acceleration equals delta V, that's change in velocity, over t, which is time. Acceleration will be measured in units of meters per second per second. If you look at the equation, that should make sense. Velocity is in meters per second, time is in seconds, so it's meters per second over seconds, which could be simplified as meters per second squared. Delta V, or change in velocity, is measured in the same units we've always used for velocity, and that is meters per second. Delta V, by the way, is change in velocity, and it can be found by subtracting your final velocity minus your initial velocity. And T is in time, and we're typically going to use seconds here. For the record, these are our standard units. You don't have to see these in meters per second per second. You could have kilometers per hour per second, and that would also be a valid unit for acceleration. It's just your velocity unit divided by a time unit. The sign of acceleration, whether it is positive or negative, indicates whether the velocity is increasing or decreasing. Is your change in velocity increasing or decreasing? Okay, so let's talk about when we have a positive acceleration. What if we have a positive number for our acceleration? This indicates that the change in velocity is positive. There are two circumstances where this can happen, and I would recommend that you write these down and maybe even the data tables that I provide as well. Okay, but whenever we have positive acceleration, that can occur when we have an object that is speeding up in the forward direction. And I think this is easier to see if we put some fake data to it. So here's an example of an object over the course of 3 seconds, changing its velocity from 0 to 2 to 4 to 6. This has a change in velocity every second of positive 2 meters per second each second. That would be the acceleration of the object with the data in that table. And that is a positive change. The second one is less obvious. But when you have an object that is slowing down in the backward direction, that is also an example of positive acceleration, and here's why. Okay, if you look at these values, again, for 0 to 3 seconds, our velocity here is changing from -12 to -9 to -6 and then -3. That is a change every second of positive 3 meters per second each second. And so if you looked at these two scenarios, these are both examples of positive acceleration. This is a very common misconception because people always think positive acceleration means speeding up. It doesn't necessarily mean that. Okay, again, this object is slowing down in the backward direction. That is still an example of positive acceleration, and here's why. Look at my change in velocity each second. Make a note because this is a very common misconception. A negative acceleration indicates that the change in velocity is negative. There are two circumstances under which this can occur. The first is if an object is slowing down in the forward direction. Again, if we look at data, we can see this very clearly. This object goes from 8 to 7 to 6 to 5. The change each second here is -1 meters per second every second, or -1 meters per second squared, which is a negative acceleration. This again is more obvious than this example down here. An object speeding up in the backward direction is also negative acceleration. Negative acceleration doesn't mean slowing down necessarily. It did here, but it doesn't mean that here. And look at my data, here's why. This object is getting faster because 0 means you're not moving. So going from a velocity of 0 to -5 means you're going from being at rest to moving, and then you're moving faster and faster. You're just doing it in the negative direction. That's all the sign means is which way. So you're going to the left, but you're getting faster. Okay, the change in velocity every second in this particular example is -5 meters per second each second, or you can write that as -5 meters per second squared. These are both examples of negative acceleration, and again, I would write them down and possibly the accompanying data tables because it is a very common misconception. Negative acceleration doesn't necessarily mean slowing down. Positive acceleration doesn't necessarily mean speeding up. And the same thing's true about direction. Negative acceleration doesn't necessarily mean you're moving backwards. Positive acceleration doesn't necessarily mean you're moving forward. Okay, there are examples here for both where we are slowing down forward or speeding up backwards. So that's both directions and both types of change in motion here, slowing down versus speeding up. Okay, so look at the numbers in this table or think of numbers in an example, or as we look through the notes later on, looking at graphs can actually help to clarify this as well. All right, here's an example problem for us to think about. It says, let's say a car is traveling at 20 meters per second and enters a freeway ramp where the car accelerates at a rate of 5 meters per second every second until it reaches a speed of 35 meters per second. What is the car's speed after 1 second after entering the ramp, 2 seconds after? So let's go ahead and make a data table. So initially, this car is traveling 20 meters per second, it says so in the scenario, and it starts to accelerate at a rate of 5 meters per second each second. That means after 1 second, it would be going 25, which, by the way, is the answer to letter A. After 2 seconds, it would be going 30 because its velocity is changing 5 meters per second every second. Positive 5. It doesn't say it's negative here, so it would have been better if I typed a plus sign. I didn't. But here you can see the change in velocity is positive 5 meters per second each second. I could even continue and say, hey, it's going 35 meters per second after 3 seconds. Since it said until it reaches 35, this would be how long it took it to do that. Okay. How does the distance that the car travels in a second change as its speed changes from 20 meters per second to 35 meters per second? This gets back to what we talked about in our last unit. To go 20 meters per second means that you travel 20 meters in a second. To go 35 meters per second means that you travel 35 meters in a second, which means the distance that the car is traveling is getting greater and greater and greater. Okay, think back to that motion map, okay, or the dot diagram on your test. Those dots were all evenly spaced because last unit everything was constant velocity. But if we're dealing with something like this, those dots would be getting farther and farther and farther apart, or those arrows would be getting longer and longer and longer because you're going from a slower speed where you're only going 20 meters each second to a faster one where you're going 35 meters each second. How many seconds does it take the car to reach 35 meters per second? In the data table we made a second ago, we saw that that takes 3 seconds. Okay, so here's a similar scenario. I've just added some other data, but it says a car is traveling 20 meters per second for 3 seconds when it enters a freeway ramp where it accelerates at a rate of 5 meters per second every second until it reaches a speed of 35 meters per second. So this is pretty much like the last example, except now I have 3 seconds of moving 20 meters per second before this starts to happen. Actually, I only have 2 here, but we're going to go with it. In my graph, it looks like 3. But it says a data table might look like this. What would the XT graph look like? And what you would see on the XT graph is you would see a straight line for the portion where you have constant velocity. After 1 second, you've moved 20 meters. After 2 seconds, 20 more. So you're at 40 meters after 2 seconds. This is what our graphs looked like last unit. But once you get to this portion where it starts to get faster, my slope has to get steeper, just like it did in the gizmo on Friday. And so the slope goes from this, straight line constant velocity to getting steeper and steeper and steeper as we get faster and faster and faster. And so whenever you have acceleration occurring on a position time graph, you will see a curve. In this particular example, this curve is showing us getting steeper, which means we're getting faster. And if we found the numeric values for the slope, we could see how much faster we're getting each second. Did we answer the last question? Yeah, we already have the graph. The meaning of the slope on a position time graph is the speed or velocity at which the object is traveling. So the changing slope means my speed is changing. I can see that in the table. I can see it in my picture, and in my picture it appears as a curve. All right, so if speeding up means that the slope gets steeper, then which of these graphs shows an object slowing down? And I have 4 choices here, A, B, C, and D. So take a moment to look at them. Maybe even turn and talk to your neighbor. Pause the video for a second if you need to. Okay, and which one shows the object slowing down? Well, if steeper is getting faster, then getting less steep or more horizontal would be getting slower. And so if I look at these options, the 2 that show a graph that is getting less steep or getting more horizontal are B and D. In both cases, my graph starts out steeper and flattens out. Now it is obviously a different shape here, but both of them start out steep and get flatter. The slope becomes more horizontal, which means the distance traveled in a second is less. This means that the speed is getting slower. What do you think the difference is between image B and D? Okay, so again, take a moment, look at these 2 graphs. We've already determined that they're both getting slower, but what makes them different? How is this object getting slower different than this object getting slower? And again, you can pause it if you need to, take a few minutes, or rather 30 seconds to talk to your neighbor and see if you guys can figure out how you would answer that question. The difference here is that this one has a positive slope, whereas this one has a negative slope. A positive slope on a position time graph, we should remember from the last unit, means we're moving forward. A negative slope on a position time graph means we're moving backwards. So object B is an object that is moving forward and slowing down, whereas object D is an object that is moving backwards and slowing down. Which graphs show positive acceleration? Again, if you would like to, you can pause it and turn and talk to your neighbor for 25 seconds. See if you can figure out which one of these shows positive acceleration. looking at these graphs, again, I can have positive acceleration under two circumstances, and we wrote them down earlier. Okay, remember, acceleration is positive when change in velocity is positive. This happens when an object moves forward and speeds up. Again, think of example numbers if you need to. But if you go from a speed of 2 to 4 to 6 to 8, so on and so forth, okay, then you have a positive change, and this is an object that's moving forward and getting faster. The graph that corresponds with that is A. Okay, but it also happens when an object moves backwards and slows down. Again, you might have to think of numbers to see this. That's why we wrote down those data tables earlier. But if you have an object that is moving at -15 and then -10 and then -5 and then 0, the change in velocity each second is a positive change. Specifically in this example, +5 meters per second every second. So if we find an object that moves backwards, and I know it's backwards because these are negative numbers, and slows down, okay, then that is also an example of positive acceleration. And the one that I see moving backwards and slowing down is answer choice D. So both A and D show positive acceleration. I do have students sometimes that use this little trick. And again, this is just a little trick to use. I don't want you to get confused by it, so you don't have to use it. Personally, I think the numbers is better, but some students think of forward as positive and speeding up as positive, but again, speeding up doesn't necessarily mean positive, but for this trick it does, and they say, okay, positive times a positive is positive acceleration. Okay, and then they think of an object moving backward and slowing down as a negative times a negative, and a negative times a negative is a positive. So maybe that little trick helps, but honestly, it's safer to go back to these numbers so that you don't accidentally reinforce some kind of misconception. By the way, this particular question is a lot easier to answer if we look at a VT graph instead of a position time graph. We haven't looked at those yet for acceleration, so we're going to go ahead and do that. Remember, acceleration is the rate of change in velocity. This means that the line on our VT graph will have a slope. Everything in our last unit, we had horizontal lines on our VT graph because last unit, all of our velocities were constant. But if we have a change in our velocity, then that's going to appear as a sloped line on these graphs. Okay, so if we want to draw a VT graph that shows the same motion as the XT graph, to draw a VT graph, ask yourself two questions. Which direction is the object going? Is it going forward or backwards? So you're going to have to analyze the XT graph to do that. So let's start with this one. Is this object going forward or backwards? I know this object is going forward because my slope is positive. And if it's going forward on a VT graph, that means that I need to draw in the positive region. So whatever I graph has to be up here. Then you're going to ask yourself the second question, is this object speeding up or slowing down? And if I look at this graph, again, this starts out relatively flat. It gets steeper, which means it gets faster. And if I want to get faster on a VT graph, okay, you need to first ask yourself this question. How fast are you going if your velocity is 0? Because that's where your x-axis is, 0 velocity. And the answer is, of course, that you're not going anywhere. You're stopped. That's the slowest possible speed you can go, is not moving. And so if your object is speeding up, you need to move away from 0. If your object is slowing down, you need to move towards 0. If it slows down all the way to a stop, you're going to touch the x-axis. Okay, with this particular graph, this object we already said was moving forward, and this object is speeding up because my slope gets steeper. To represent speeding up, I need to move away from 0, and again, it needs to be in this region because of the answer to the first question. The object is in the positive direction. So the VT graph that matches this XT graph would look something like this. Now let's do the same thing for graph D. This object, what direction is it going? Is going backwards. I see a negative slope, which means backwards is down here in the negative region of my VT graph. Is it speeding up or slowing down? This particular object, my slope starts out rather steep and it gets pretty horizontal, which means it goes slower and slower until it probably stops. So it's slowing down while going backwards. Backwards is here. Slowing down means we approach 0. Because you can't go slower than stopped. Okay, so this would be the graph that corresponds to this position time graph. Here's your matching VT graph. Again, you need to be able to do this. By the way, the slope of the VT graph is your acceleration. This slope numerically, if we calculate what it was, if we had numbers, it would tell us what our acceleration is. So maybe this object's velocity is going from 0 to 2 to 4 to 6 to 8, just like those tables we looked at. This would go from 0 to 2 to 4 to 6 to 8, and the slope of that line would be positive 2, and that would be my acceleration. Whereas this object might be going from negative 20 to negative 15 to negative 10 to negative 5 to 0. Okay, again, we already talked about objects that are moving backwards, slowing down. But the change in that each second is positive 5 meters per second in that particular example, and that would correspond to the slope of this line. So if you find the slope of a VT graph, that slope represents your acceleration. All right, we're going to sketch out examples of every possible type of motion. Again, I would recommend that you copy these into your notes. The first three will look very familiar. We've already talked about objects that are not moving. If they're not moving, then we have a horizontal line on our XT graph. If they're not moving, they have 0 velocity, so you're going to have a horizontal line at your x-axis. And of course, if you're not moving, you're not accelerating either, and so that will also be at the x-axis with a value of 0. Velocity is 0, acceleration is 0. Second type of scenario would be if you have an object moving at constant velocity forward. Constant velocity forward in an XT graph, I show constant velocity with a straight line forward with a straight line that has a positive slope. And it doesn't have to be here. It could start at 0. It could start way up here. It could even start down here in the negative region if I had it included. Okay, but as long as I have a positive slope and a straight line, then I have something that is moving at constant speed moving forward. The velocity of this object would be positive. Again, the slope of this graph tells me my velocity. We talked about that in the last unit. Okay, so if this has a slope of positive 3, then this is at positive 3. Okay, but this object here has constant velocity. This graph looks familiar. We did them in the last unit. There's no change in my velocity, so my acceleration is 0. The slope of this line is 0. The value of acceleration is 0. Positive velocity, 0 acceleration. The last graph that should look familiar is this one. What if you're moving at a constant velocity backwards? Backwards just means negative slope on my XT graph. So this would be an example of something moving backward with a constant velocity. Again, the slope of this line will tell me my velocity. So maybe this has a slope of negative 2. Well, then this would be at negative 2 on my VT graph. But it's a constant negative 2. It's negative 2 the whole time because I have constant velocity here, which means I have 0 acceleration. So the rest of the graphs are going to be a little bit new for us. This, by the way, is negative velocity, 0 acceleration. Okay, speeding up while moving forward. We've seen examples of this today. You saw an example of this in your gizmo. But if I want to show something is speeding up moving forward on my XT graph, first of all, forward means positive slope, but my slope has to change because I'm getting faster. And getting faster means getting steeper in terms of a slope. This would be an example of an object that is moving forward and getting faster, speeding up. On my VT graph, I now have a change in my velocity from roughly 0, because it's pretty horizontal here, to something pretty fast. And so to show something speeding up moving forward on my VT graph, I would have something like this. Okay, again, I would start close to 0 or at a lower numbered velocity, and I would get faster and faster and faster moving away from 0. Now, in this course, we only deal with uniform acceleration, which means that if we have acceleration, then our VT graph will only ever have a straight line. I'm not going to give you a curve on a VT graph. Your change in velocity will be a constant change each second. Okay, but this change in velocity maybe is going from 2 to 4 to 6 to 8 to 10, which means that my acceleration within that example would be positive 2, and I'd have a line here, a constant positive 2 meters per second every second, for example. But again, the slope of my VT graph tells me my acceleration. This is a positive slope. Therefore, this is a positive acceleration. Positive velocity because I'm in the positive region. I'm moving forward. Positive acceleration, I'm in the positive region. What if I speed up moving backward? Okay, so if I'm moving backward, again, I need a negative slope. If I speed up, that means my slope has to get steeper. Something like this would be an example of something moving backwards and speeding up because it's starting out with a relatively low velocity. Maybe it's 0, maybe it's just above it, and it gets faster, but in the negative direction. To show something going backwards, speeding up, backwards, first of all, means I'm down here, but speeding up means move away from 0. Needs to get farther and farther away from being at rest, just like this was at rest and got faster and faster going negative. Again, the slope of this line tells me my acceleration. This line has a negative slope, therefore I have a negative acceleration because my velocity might be going from 0 to -3 to -6 to -9 to -12. And if that's the case, my change each second is -3, and so I'd have a line here at -3. This is an example of an object with negative velocity and negative acceleration. By the way, another helpful trick to remember, if your velocity and acceleration are in the same direction, meaning they both have the same sign, negative velocity, negative acceleration. If they have the same sign, you will be speeding up every time because that means they're working together. You're already going this way and it's getting more that way. So you're going to speed up. If your signs are opposite, then you're going to slow down. Okay, so slowing down, moving forward. Again, forward on my xt graph, positive slope. Slowing down means my slope needs to get flatter, and I'm going to have a shape like this. Going forward on my vt graph means I'm up here. Slowing down means I need to get closer and closer to 0 because that means I'm not moving at all, and that would be the ultimate slowdown is if I stopped. So this would be what my vt graph would look like. Okay, again, the slope of my xt tells me my vt, but my slope here is changing. It starts out relatively high, and then it's kind of medium, and then it's kind of 0. And that's what this shows, high, medium, 0. There's no numbers. Okay, same thing here, though. The slope of this tells me this. This has a negative slope, therefore this is a negative acceleration. This particular example shows an object with positive velocity because it's moving forward, but with negative acceleration. And just like I mentioned a second ago, if your signs are opposite, positive velocity, negative acceleration, they're working against each other, you're going to slow down. Okay, so if you see that, you're going to be slowing down. All right, slowing down, moving backwards. Again, backward is a negative slope. Slowing down means that that slope has to get less steep, has to get flatter. It'll look something like this. Okay, to show that on my VT graph, backward is down here. Slowing down means I need to approach 0 like this. The slope of this line tells me my acceleration. Okay, again, if I'm slowing down, moving backward, maybe I'm going from -5 to -4 to -3 to -2 to -1 to 0. The change in velocity each second in that particular example would be +1. And again, you see a positive slope. That slope will correspond with the value for this. This particular example is an example of something with negative velocity and positive acceleration. Again, opposite signs mean I am slowing down. All right, guys, those are all of the different types of graphs that you might see. Of course, you could see some that are more complicated that show, a sloped line that then goes flat or whatever. You have stages, but for today, you're going to be working on My Open Math Assignment 202.1 Acceleration Concepts Problem Set. It is due by 11:59 p.m. tonight. You may work together. You do have randomized questions, so just keep that in mind, but you are welcome to help each other. I would recommend that you have out paper for any questions that have any part of math in them. There might be a little bit in there, but this is your assignment for tonight. So go ahead and work on this in class, and anything you don't finish, you can do at home by 11:59 p.m.